For over a century, railways have spanned the land of Britain, linking together people and places. They were built by civil engineers, men who looked at the land and decided where the line should go, seeking firm ground and easy gradients. But they could not always build railways on the natural surface of the soil, and there are barriers they could only overcome by moving earth or building structures. The railways they built are part of the landscape of Britain. We see the work of civil engineers on every side, and if we go back 100 years, we can discover how they carried it out. The railways were built by men with spades and shovels, a few horses, and primitive equipment. This was all planned and organized by some of the first professional civil engineers. The men who gave us the greatest railway system in the world.
Now we're bringing up to date our railway system under the Railway Modernization Plan, with its great program of civil engineering.
I'm opening up a bottleneck at Potter's Bar that holds up trains on one of the main lines up to London. A lot of our work is moving earth, but we've replaced the spades and barrows of the pioneers by machines. London clay is hard work, and we've got bulldozers, mechanical shovels, a light railway, and even a bonus system.
"200 miles further down the same line, we're using a more specialized machine, which only needs one man to control the whole operation. Still further north, on the edge of the Highlands, there are more machines. In the last century, many railways competed against each other here, and we're streamlining the results of that rivalry. We have to clear and flatten this great area of land, besides diverting a small river. Bill Wood is the resident engineer, and is responsible for checking every detail as it is carried out, and planning the execution of the work as a whole.
Right.
What I've had to do here is to measure out the ground and fix posts to show where we have to build up the level. The lie of the land varies, and here there's less to do. Johnny Patterson is cutting the tops off any humps and using that earth to fill holes as he goes along. Caterpillar tractors can go almost anywhere in any weather, but look how much faster the new rubber-tired machines can travel when the weather's fine.
We are preparing the ground for over 60 more sidings near the steel mills of South Wales. This is a very different job, for there are extensive sand dunes, and most of the site is made up of blown sand. The engineers here feel rather like the walrus and the carpenter, who wept like anything to see such quantities of sand. If this were only cleared away, they said, it would be grand. If 7 maids with 7 mops swept it for half a year, do you suppose, the walrus said, that they could get it clear? We haven't got 7 maids, but we've got 7 diesels, and we're well on the way to building one of the most up-to-date railway marshalling yards in Europe. We've just finished one in Scotland, so let's see what all this marshalling yard work is leading up to. Here at Thornton, the yard is for making up trains to carry coal from this new pit of the National Coal Board. The latest equipment has been fitted in our control tower. There are television cameras to overlook a wider area, and radar helps in controlling the speed of wagons as they pass through automatic retarders. But a marshalling yard depends above all on civil engineering, for there must be a reception area large enough to take in several trains of empty wagons every day. And the rest of the yard must have plenty of room for making up many trains at the same time. While the gradients must be worked out, so that any wagon can roll under its own weight from the top of a hump to the furthest part of the most distant siding. A lot of our work is moving earth, but there's another side to every job that starts long before the machines. This sharp bend slows down the Golden Arrow as it passes through Chislehurst. A smoother, much faster curve has been worked out on paper. But before any earth is moved, Jim Moorhead has to mark out the new curve on the ground.
I suppose the old line was marked out in exactly the same way. But even if they had to ride here on horses, they didn't have to worry like us about working on a busy railway. My chainman has to look out too for the live rail. He'd be in trouble if he used his ordinary steel measuring tape. We mark each point to a fraction of an inch, for a great deal depends on my accuracy.
So anyone who wants to be a civil engineer must learn to use this instrument, the theodolite. That's one of the first things we teach at our Paddington school. For when we make maps or plans, we use a theodolite to fix the position of objects on the ground. Every civil engineer has to have a great deal of training, and we've specially picked every boy in this school. He's got at least 5 years' hard work ahead of him before he can become an associate member of the Institution of Civil Engineers, which is our recognized professional qualification. It is when he can put the letters A-M-I-C-E after his name that he'll know that he has really arrived. When he learns to use a theodolite, he also finds out how to put the results down on paper. There's a lot of paperwork, but in the years ahead, lives and lots of money will depend on his plans. He must be as good with a pencil and paper as a surgeon with a knife. And as it happens, it takes him just about as long as it takes a doctor to qualify. All our students go right back to school and learn to write clearer than they've ever written before. We're also training drawing office staff, because they do a lot of the paperwork. But every qualified civil engineer must be skilled in surveying and a draftsman in his own right. A great deal of time goes into teaching our students to use their hands. But they must spend many evenings getting things into their heads. And one thing they all learn about is the soil itself. We've accumulated a great deal of knowledge about soil from our past experience. But the quality of soil is almost infinitely variable, and this is where science comes into the picture. Soil mechanics is a growing branch of scientific research, and in our new laboratories we are obtaining information which saves us a lot of the time and money that we used to spend on tests and experiments in the field. John Pellow is measuring the strength of the clay on one of our sites on the western region, so that our civil engineers will know exactly how they can use it to build on. The carefully prepared sample of soil is surrounded by water at a constant pressure. And when he switches on, a screw forces a large vertical steel ring down onto a plunger on top of the soil. The ring is compressed between the screw and the plunger on the soil, and a gauge measures the distortion. Then as the load goes on increasing, the soil starts to give way. And in the end there is so little resistance that the ring stops deforming and tends to return to its original shape. From such a graph, we estimate how any particular soil will stand up to any load. The soil at Gloucester did not stand up to the load of this viaduct, and trains are forced to slow down and crawl along the uneven track. We have to cope with this problem and build a new viaduct.
I'm using piles to build on. We've made tests, and each pile is designed to a calculated strength and size. It doesn't take much to drive them through the soft soil near the surface.
We've seen how we survey the ground and prepare it. Now let's see what we do on top of it. A great deal of our work is concerned with railway lines. We use machines to pack the ballast which holds the lines and sleepers in position. In many parts of the country, we are busy replacing some of the shorter lines of the past by long lengths of smooth welded rail, here being laid straight into the chairs. This great advance has been made possible by modern equipment coupled with scientific research. In this special laboratory, we are testing new ways of fixing these long rails by measuring what happens when we heat them until they buckle.
Temperature number 16, 69, vertical gauge number 16, 0098. Number 21, 0090. Number 21 is moving quicker. 0188, 0187, 86, 85, 84, 83, 81, 80, 79, 78.
But our scientists cannot measure everything they'd like to in even our largest laboratories. And we want to know, for example, exactly what happens when trains pass over any of our bridges. Chepstow Bridge has been in service ever since Brunel built it 100 years ago. And this complicated structure still carries our far heavier trains. It is impossible to calculate on paper exactly what is happening. Today, John Lucas from our Derby Research Department can make an accurate measurement of the slightest stretching or compression of the metal. He has polished up the surface of a part of a girder and is now coating it with a very strong cement. He places a strain gauge in position. This is a thin piece of plastic supporting a fine metal grid through which a current of electricity will flow. Another layer of cement goes on top. This is such a good adhesive that the gauge will be virtually part of the metal of the bridge. The only way to remove it will be by grinding it off. There are 46 of these gauges on selected measuring points, and wires from them all lead into a wooden hut at one end. Inside the hut are the recording instruments. All the gauges are carefully balanced so that the relative movements of many parts of the bridge can be recorded simultaneously on film by moving spots of light. Each moving spot is recording what happens as a part of the bridge is stretched or compressed. We discovered from this that there is no movement liable to cause serious fatigue. So far, we've seen how we prepare the ground to carry the lines. This is the site of a new motive power depot at Thornaby, near the mouth of the River Tees. We've covered the flat marshy ground with slag and calculated that these small platforms will take the weight of our lighter buildings. But for the heavier ones, we've sunk piles, and we're chipping away the tops to expose part of the reinforcing rods. The ground is waterlogged, but those rods will be bonded into the concrete of our new buildings, and they will be as firm as a rock. Pre-stressed and reinforced concrete are some of the most exciting media we use, for we are discovering new possibilities every day. We've used concrete in our new diesel sheds at Darlington. The roof is built with slender beams that admit plenty of light, while the floor has the rails mounted with far more working space underneath than in any of our old sheds. On the flat fenland below Lincoln Cathedral, we are building one of the largest goods sheds in Europe. We chose steel because of its combination of strength and lightness. A concrete frame would be much heavier and need more piling in this soil. A gusty wind is always a headache and can bring a job like this to a standstill. It's only when everything is just right that we can bolt the sections together ready for welding. At Banbury, there's a real adventure in design, for we are using concrete, steel and glass to build a completely new station, with plenty of space and light for our passengers to move about in. In nearly all our work, we have to face special problems. Our picture wouldn't be complete if we didn't show you the sort of problems that crop up in railway work. This isn't an ordinary bridge, for below the ground lies one of the richest coalfields in Scotland. And as the coal is taken out, so the surface will sink. This was the problem that faced our resident engineer, Alan Jackson.
This ground will subside 11 feet in the next 30 years, and I'm checking how far it's fallen since we started work here. We've designed the bridge so that it can be lifted up as the ground goes down, and that crack in the decorative block, which can be easily replaced, shows the bridge has moved already. The main platform does the work, and a thin layer of felt between it and the supports permits some movement without damage. As the sides sink, the main platform can be raised from several jacking points and built up underneath. The center of the bridge is fixed to trestles, and these too can be lifted up to allow new sections to be bolted into place below.
A more general problem we face is that great armies of labourers are no longer available to build our railways. A vast number of bricks were used in the original tunnels at Potter's Bar to withstand the pressure of the surrounding clay. We are driving new tunnels alongside the old, but we are lining these with prefabricated sections.
It was decided to make the parts of concrete and to build a factory right on the spot. The mixture is made up by weighing each part automatically into hoppers. A button is touched and the exact quantities drop onto a moving belt and are carried into the mixer. Each batch is just the right amount to make one section. These sections will form the walls of the tunnel, while in another shop we make parts to form the base. Inside the tunnel, the large steel shield that we drive into the clay has been fitted with hydraulically operated arms to lift the sections into place. The more traditional methods took hundreds of skilled bricklayers to build walls as thick as these. But with modern equipment and materials, a few men do the work and in a fraction of the time and cost. Even while sections are going into place, men are working inside the shield, removing the earth it has cut and shoveling it down onto moving conveyors below.
But our greatest problem never faced the pioneers, and makes modern railway work some of the most difficult and fascinating of all civil engineering. We have to do our work on the most heavily used railway system in the world. We are building a flyover and a dive-under at Barking, where the Tilbury, the Southend and the Upminster lines cross.
I'd call this a straightforward piece of engineering, if I could stop all the trains and do the job. But no, people must go to work, and the trains have to keep running, and it has taken me months of shifting tracks to get room for these concrete piers on the left. I've only just won this little island for my piling frames. The dive under is held up until I can move the lines at the far end somewhere else. Soon I will be able to put trains on this track and get one more little bit of valuable working space. But first I have to get the new line over the river.
We are proud that this work is in the tradition of the great railway builders, like Brunel, who carried the railways over his bridge at Saltash down into Cornwall. Robert Stephenson, who spanned the Menai Straits with his tubular bridge and crossed the Tyne with a high-level bridge and its roadway suspended below. His father, George Stephenson, and the other great civil engineers of the 19th century, whose profession was defined in the Royal Charter of their institution as the art of directing the great sources of power in nature for the use and convenience of man.